can just stop sharing now.
Oh, but I need to share with during the talk, right?
Okay, so now let's welcome Anna Chi, software engineer at UiPath. She's going to walk us through how to build efficient image processing pipelines, which are very crucial for training multimodal LLMs and working with visual data at scale. Go ahead, Anna, the floor is all yours.
Mm-hmm. Um, Hi everyone, I'm Anna. I'm a software engineer working in UiPath now. I used to work at Amazon for a couple of years, and where I was involved to build the large-scale image processing pipelines to support the Amazon AI training. And there was like billion scales of data. Um, and at Amazon, we valued frugality a lot. So it's kind of not contrary to what people assume. Like we don't have the unlimited AWS resources to play with. We were kind of like requestly asked to optimize the compute, the storage, and the bandwidth because like cost at scale add up very quickly, and we can end up burn up a lot of money for the company without knowing it. Um, and they don't also allow us just throw tons of GPUs for every problem. Well, that is the easiest way to solve the problem. So because of that experience, it kind of helped me shift me how I think about this building, how important to build a very efficient, effective, um, uh, financially affordable image pipelines. They have to be fast, scalable, and cost conscious. So today, I'm gonna walk through some practical ways to build the pipelines that are not just functional, but also financially affordable. Let me share the slides really quick. Okay, cool. Um, so let's see. So this is the agenda. So we are gonna start with some use cases, what I have been solving the problem with, the challenges that we've been through, and kind of like the state of the art solution that will be adapt and the future innovation for what we're gonna go from there. Like image data is core to a ridiculous number of industries. Like we have like autonomous driving, like each camera generates like 30 fps. There's thousands of images per second that need to be labeled, filtered, analyzed. Healthcare is one of the things we look at a lot with the medical images, MIRs, CTs, X-rays. File sizes are huge, and those file sizes need to be very precise and with a lot of accuracy image data. And e-commerce, like we deal a lot with Amazon. Every product comes at least like 3 or 5 images. And these days, there also need to be millions of resize, compressions, conversions, and storage operation. And you can have just one image, but with different, maybe like at least tens of them copies just for different criteria of the images. And social media. Uh, Amazon didn't do a lot of social media yet, but in the last stage when we're doing this image, building this image data, we did apply to a lot of pictures and videos, short video, TikTok, um, and of course, this is like need a high stake infrastructure, and if you are doing the efficiency, it will get the regression quite quickly. So now we understand like how critical and widespread the images pipelines can be used at. Let's get into what's kind of the major challenges, and some of them are really easy to be overlooked. Um, yeah, there are like four main challenges with the images pipeline that kind of whenever you think about it, these things you need to answer right away. And also you need to solve it right away at the early start, because later on it's kind of very expensive to revisit. Storage, which is can be like high resolution images. And here we are normally talk about at least 5 MB. Um, and based on that, you need to multiply by thousands of daily uploads and batch jobs. And to give an example, at Amazon, we had this pipeline. We switching from PNG to WebP saved, WebP, and then this is saved about like 60% of the storage volume, and with zero visible quality loss. That helps thousands of hundreds of savings in our annual cost. And then the computation, we have lots of tasks. For the image, you have lots of tasks that you need to do with resizing, filtering, inference, or converting formats like GPU and CPU intensive. If you're not batching efficiently or offloading to accelerators, we are gonna wasting lots of cycles from there. There have been a time that we spent thousands a month just running image transformations on some general purpose EC2 instead of the GPU backed one. And yeah, that's a bit hassle for us to parallel the workloads after. Excuse me. And the third one is the processing times. For the real-time systems, even some small delays can compound very easily and exponentially. Like think about this kind of live preview generation we are doing, the moderation or tagging, just want to tag some images and annotate them. The operations need to take within a second. Otherwise, otherwise the customer's like drop down conversion will be dropped down very quickly. And the last one is the bandwidth. This is kind of hidden, like you only notice when you're actually serving the product traffic. But this is more like serving bloated images on web or mobile, tax performance and burst money, especially on mobile. Even like 1 MB versus 200 gigabytes per image has massive downstream cost and latency implication. These bottlenecks not just hit separately, they always hit together. So sometimes you have a you have a problem, it doesn't scale or it doesn't perform as you expect. It can come all of them, not just one. And because it come all of them, it's really hard to know what exactly going on. So most of the cases we have just end-to-end rethink of the pipeline, what can go wrong. But if you know the general principle, it can be layered in it can fall into one of the four majors, then it will be much quicker and easier to spot the issue. And now we know what's the challenge. Let's jump into like define what kind of the success criteria and the goals we want to achieve with this images, with this efficient and frugal pipelines. We want to minimize processing time by parallelizing and optimizing. Optimize resource utilization via serverless GPUs or batching operation. Reducing storage and delivery costs by using smarter formats or compression. We are not building something a luxury product. We are building something hybrid, fast, lean, and affordable. And yeah, let's start with the foundation from here. Picking the right image format. It sounds boring or simple, but it's the first and often most overlooked decision that will determine the pipeline performance and the cost baseline. As you can see, there are tons of formats that we can choose from. And Yeah, and actually based on different stack or purpose, you might choose different formats based on your needs. But we can say JPEG can be a general good start. It mostly like works in different cases. But AVIF and the WebP will save more real money if we want to serve the image at scales such as like millions or billions. Um, yeah, we can go to the JPEG first because it's still the most widely used format and simple to start with. Let's understand what does well and what falls short. And then from there we can start to see if how we gonna do it compare with the newer modern formats. JPEG is kind of a lossy format. It's very good for photography content. It allows adjustable quality levels, which helps balance visual fidelity with file size. For example, if we are like you lose this Python library, if we're saving the quality at 75, often reduce the file size by like 50%, while still keep the image visually acceptable. It's universally supported and works great for user uploaded photos, product images, and anywhere where perfect accuracy isn't required. But it doesn't handle transparency or sharp edges very well. That's where PNG is mostly used, or YP take over. No, yeah, we can take a no. Speaking of which, yeah, we can take a closer look at PNG, when to use it and why it's often misunderstood in performance-sensitive environments. As for JPEG here, we just like it starts to fall apart when you need transparency or pixel perfect detail. For example, you need to do some machine learning algorithm or more advanced image recognition on the picture later. So with that, you probably need PNG to start with. With JPEG, it became bit blur and it lose the key information of the picture, and later on the vector, if you want to use this vector search or machine learning to extract the key information, it can be very buggy. PNG is lossless image format. It preserves all visual information with no compression artifacts. It supports transparency and ideal for images with sharp edges like UI icons, logos, diagrams, and screenshots. But of course, the trade-off is it's very heavy. It's like 1,000 by 1,000 PNG might be like 1.2 megabytes, while the same image with WebP could be 300 KB. So we tend to use PNG when the fidelity is very critical, such as when we want to search some celebrity image or some very good quality image on some especially experience. Um, and if you are optimizing for web or mobile, use PNG8 for simple graphics like icons. This limits the palette to 256 colors and can shrink the file dramatically. Don't you try to avoid using PNG for photographic content unless absolutely necessary, because it will eat the bandwidth quite quickly. And now we are covered the legacy formats. We can start to look things more trendy and modern, which I mentioned multiple times already. WebP, AVIC, and I still don't know how to pronounce it quickly. HEIC or HEIC, which the Apple Photos format that's on your phone. This offers significantly better compression, and we can understand how is it compared to modelize our image pipeline. P, AVIC, or AVIF and HEIC are modern image formats that offer significant advantages in both compression and performance compared to JPEG and PNG. To do a very simple number like for the same same quality of image, JPEG can be 100 KB, while WebP will be 70, and AWAV will be 45. That's like a 55% of reduction in size without any perceptible visual loss. And the savings scale dramatically across millions of images. You can see the graphic, the metrics will be differ a lot. To give more details, WebP supports both lossy and lossless compression, as well as transparency. It's widely supported across modern browsers and works great for a web app. AWAV is based on the AVI video codec and offers even better compression than WebP. It supports HDR transparency and has a much higher compression efficiency, but it's slower to encode and not yet supported in every toolchain. Hake uses the HEVC compression and is the default format on Apple devices. It's efficient and high quality, but less transportable or interoperable outside Apple ecosystem. These formats are where the industry is headed. If you are building a modern apps, WebP or AF should be your defaults. Okay, now like we have already looked at these formats, we can understand. It's very important for us to understand the key difference that underpins all of them, like whether a format is lossy or lossless. That distinction will shift what format to use for which use case. Lossy compression throws away some information to reduce size. It's based on how human eyes work. We are less sensitive to fine detail in color gradients. For instance, this means you can compress a 1 megabyte image down to 100 kilobytes or less with very little perceptible difference. Formats like JPEG, YP, and AF use this approach. Very perfect for user uploaded photos, product listing, and social feeds where small file size and fast delivery matter more than precision. But for lossless compression, retains all the image data. What you compress is what you can perfectly reconstruct. Like PNG, TIFF, and AF useless all for this camp. You use this when pixel perfect accuracy is required. For example, UI assets where anti-aliasing matters, diagrams or CAD exports, medical images, which I just mentioned about, use very expensive and very good, very cool to look at when you apply it well. With this diagnostic accuracy is very critical. There's one scenario. There's one incident I like to share. One team I work with accidentally applied lossy compression to high resolution retina scans, and this visual loss wasn't obvious until the QA check caught it and caught like a very subtle blur. And the results, yeah, they have to reprocess over like 3 terabytes of raw medical images data because that wouldn't make that would impact the future machine learning algorithm drastically. So yeah, from this story, we have to know your compression model before we start transforming images. It saves time, credibility, and compute. Now we are covered when we when to preserve every pixel and when it's okay to let some go. Let's talk about the tools, the compression method. Because like the wrong library can also balance. Like even you pick a good format, if you pick the wrong library, you kind of lose the benefits. So for so we can to get started with, For JPEG compression, like Lib JPEG Turbo is one of the fastest encoders available. It uses SIMD instructions and is optimized for speed. It should be the default for any JPEG heavy workload. Most JPEG also improves. You can also most JPEG also improves JPEG file size even further by applying more aggressive quantization and progressive encoding. It's a drop-in improvement for better compression with nearly the same quality. And for batch operation, we normally start with image magic. It's like the Swiss Army knife of the image tools. CLI based and supports nearly every format. It's great for automating format conversion and recess jobs in a CI pipeline or cron job. In Python workflows, we use Pillow a lot. It wraps libjpeg, libpng, and others. It's great for inline images handling in web apps, ML pre-processing, and microservices. The key things is try not to handle compression logic. Like every time like I have teammate want to write down some customer image encoding logic in NumPy, and somewhere it's just a bug somewhere in the later on like operation excellence, there's something coded there. Oh, you cannot do that, either the incompatibility or it impact the performance later on, or when some lousy encoding that we couldn't figure out why it just jumped there in the log splash outwhere. These libraries are very fast and robust and deeply battle test, so try to do it more native as native as possible. After the library, there's another layer of efficiency that we can unlock is by adjust compression levels dynamically based on the image content. And that's why the advanced technology adaptive compression comes in. Adaptive compression means dynamically adjusting how much you compress different regions for an image based on context sensitivity. It's the equivalent of tuning the bitrate on a per object basis. On a high level, it is like we identify important regions in an image, either faces, text, product edges, and then we apply less aggressive compression there. Backgrounds, gradients, or low detail areas get compressed more. This approach is heavily used by also other companies such as Netflix. In video, they compress backgrounds at higher ratio while preserving quality in faces and fast motion zooms. In static images, these translate to things like preserving brand logos, faces, or UI elements while cutting file size everywhere else. From a tooling perspective, you can use OpenCV to detect edges of faces, split the image into tiles or segments, apply different compression settings per segment before merging. You can also apply machine learning to classify image zooms based on the importance and the salinateness. This gives you the best of both worlds, like smaller files, no visible quality loss. Yeah, this is just like all theoretically. Now we can talk about a bit more like what it look like in action, step by step. So to like for an example, like we from what we have been doing, like first we run an object or edge detection. You can be like OpenCV or simple ML model. We're just using OpenCV because it's open, and to find areas of interest and to find areas of interest, and then we tag zones such as foreground elements, faces, logo, and then we assign per region compression quality. For example, compress the background at quality 30, but compress the detected face at quality 80. And then we recombine and encode the image. The end result is like smaller file that still feels high quality to the user. And it's quite easy for static image pipelines with this library. And now we are finished like talking about how you're gonna optimize the image level. Let's shift gears to where we actually store those images, because storage is a lot of money. Although there's a lot of cloud storage that say, oh, it's super cheap, you can store so many things, but when you actually reach that scale, the storage can still the biggest cost of it's one of the biggest cost. And also storage strategy plays a huge role in long-term cost control and scalability. And see, cloud storage is the backbone of our image pipeline. And you need to pick the right tier and the lifecycle policy can have a massive financial impact. Very common object storage service like Amazon S3, Google Cloud Storage, Azure Blob Storage. These platforms are quite reliable, scalable, and support tiering. This means like you can store frequently accessed files in hot storage and older and less used files in colder tails like S3 Glacier and GCS Codeline. What makes this the powerful of this is the automation. Set lifecycle rules to auto transition all data to cheaper storage tiers after a defined period. For temporary assets like thumbnails or intermediate outputs, auto delete them after a few days. To give an example, in one project, we have like 10 terabytes of archived image data, and just moving it from S3 standard to Glacier dropped our monthly bill from 300 to like 30, like 10. Although it's a small number for us, but still it's like 10 times cheaper. Think about if you if you apply to more petabytes bill of data, that can have a big impact. And what's good about this change doesn't require any code rewrite, just some good cloud hygiene and awareness of what's really active and what's just sitting there, and boom, switch, and the technology all did that for you. But storage is just the half of the key point. Once the image lands in our bucket, something has to process it, and that's where the serverless compute shines. Now let's look like how we can automate image tasks with on-demand and scalable functionalities. Serverless is a great fit for image pipeline because of its elasticity and pay-as-you-go model, such as AWS Lambda, Google Cloud Functions, Azure Functions to handle the bursty, event-driven image tasks without provisioning or managing service. These uses you can do with resizing image on upload, converting formats, generating thumbnails or preview versions, running lightweight classification or tagging workflow. These functions can be triggered directly by file uploads to cloud storage, making them ideal for asynchronous high-volume pipelines. For example, if you process like 100 key images over a single weekend using AWS Lambda, the entire cost, including storage, compute, logging, came out just under $10. If you compare to running the same job on a T3 medium EC2 instance for 24 hours and which can cost like 10 times more, and it need manual scaling. Serverless is really good when you need flexibility, scale, and simplicity, but you need to be aware of the cold start and execution times limits if you are task heavy. Although the serverless is great for lightweight images tasks, sometimes we still need something more powerful, especially for tasks like face detection, object labeling, or context moderation. That's where the cloud-based image processing APIs come in. Let me see. Sometimes, like building your own computing vision models or image classify isn't worth the time and cost, especially if you can leverage those powerful, scalable APIs from major cloud providers, such as Google Cloud Vision API, AWS Recognition, Azure Computer Vision. They offer capabilities like face detection and analysis, um, object and label detection, OCR, which is optical character recognition, now say for word context moderation. If the use case is common, like just labeling images, detecting peoples or logos, or extracting text, this API can save months of dev time and tuning. For example, instead of training and deploying a YOLO V5 model just to detect text and faces, you can send the images to an API and get results in milliseconds. It supports batch processing and integrates easily with the service flows. One team I work with, I just thought about like they replace a hand-tuned PyTorch model with recognition and saved both compute costs and maintenance overhead. Unless you have a very specific requirements, these API are kind of good enough for 80% of the real-world problems. So of course, these API are not that cheap. So next we are gonna talk about how to keep that keep the spending under control while still scaling efficiently. That's the cloud cost optimization. Because cloud is only cheap if you treat it cheaply. There are three key levers that we can pull. First, um, spot spot instance. Use them for non-critical, interruptible jobs like batch image processing. They are like 70 to 90% of cheaper than on demand. Second, reserved instance. If you have predictable workloads such as nightly pipeline job, reserve compute ahead of time at a discount. And third, cloud native monitoring tools. Set up budget or GCP like AWS budget or GCP quotas to track usage and set alerts. Use tagging aggressively to allocate costs by team, feature, and environment. So remember to separate the cost. So you can easily to pin down what is more costly and how to optimize. And now, we talk about how we get the spend. We can talk about, then we can more focus on how to scale, specifically how to process massive volumes of image efficiently using data parallelism. Data parallelism is about taking a large data set and dividing into chunks so that each worker processes a different portion of the data simultaneously. For our image pipelines, this might look like splitting a directory of 1 million images across 10 workers, and each worker resides, compresses, and runs inference independently. There's tools like Dask, which is allow easy integration with Panda-style workflows and can parallelize with minimal code changes. Ray is for building distributed pipelines for Python and gives you more granular task control. Spark handles massive batch jobs and can scale across clusters easily, though it's heavier. We can run a job to resize 1 million product images. Originally, it took like 10 hours on a single machine. After applying Ray to chunk and distribute the work, it dropped like 40 minutes. That's like 15 times improvement without rewriting the core logic. Just have better execution strategies. The key to assess here is stateless operations, constant batch size, and predictable error handling in each worker. That's data parallelism. So this is data parallelism, dividing the work across many workers doing the same job. But sometimes your pipeline isn't just repeating the same step over and over. It's chaining different tasks together. And that's why task parallelism comes in. Task parallelism is about running different stages of your pipeline in parallel, rather than splitting the same task across multiple data chunks. Here's how it works. Worker A resets the image. Worker B takes the reset and extract features using ML model. Worker C takes the output and uploads to storage and takes it in database. Each worker is responsible for a different task, and they are often connected using a message queue like RabbitMQ, Kafka, or just native support in workflow agents like Airflow and Prefect. This setup is particularly powerful when tasks vary in complexity or resource demands. For example, resizing might be fast and CPU light, while feature extraction is GPU heavy, and uploading is IO bound. So by separating them, we avoid bottlenecks and maximize the throughput. We use this approach in a content moderation pipeline where one service classifies the image, another generates an audio trail, and a third publish real-time alerts. Each task running concurrently, independently, and efficiently. And now we'll see how task parallelization helps divide the work across different stages. The next step is choosing the right framework to run this task. It could be Ray, Spark, Dask. The choice can also influence how easily we scale, maintain, and tune our image processing pipeline. When choosing a distributed processing framework for image pipelines, it's very important to match the tool to your use case and engineering strength. Ray is very good. It's good for developers who live in Python. It's lightweight, integrates well with the machine learning workflows or machine learning workflows, and lets you build flexible and task-based pipeline without dealing with heavy infrastructure. It's ideal for microservice pipeline, or anything involving model inference alongside image transformations. Spark is mature and high throughput framework built for big batch processing. It scales well on large clusters and supports advanced ETL, SQL-like operations, and integration with data lakes. But is GVM based and can be overkill for simpler image tasks, unless you are processing at very massive scale. Think of hundreds of millions images in enterprise environments. Dask is like more Python-like Spark, especially good for teams already using Pandas or NumPy. If you are working with a tabular metadata alongside images and want to parallelize Python-heavy workflows, that is a good fit then. Each tool also have their trade-off. For example, use Ray when you want Python native dynamic task distribution, and use Spark for heavy fault-tolerant batch jobs across large data sets. And use DAS if you're scaling up scientifically and data science workloads that already depend on Python. But in reality, we actually just choose what the skill set of our team and the complexity of the. I think the skill set is most common. Like people with the most experience will choose it, as it will be easiest and the most reliable. And once we choose the execution framework, next thing we need to talk about how to deploy and run it. And that's where the containers and orchestration tools step in to keep things reproducible and scalable. Containerization with tools like Docker lets you bundle your code, dependencies, and environment into a single portable unit. This ensures consistency across developed, testing, and production environments. For orchestration tools like Kubernetes, this is the standard for container orchestration, auto-scaling, fault tolerance, and provide the rolling updates. Uh, the second tool I think of is like AWS EC2. It's simpler setup for AWS native environments, or GKE for Google Managed Kubernetes Service. So when we talk about these benefits, like be sure like we know about reproducible, the code runs the same everywhere. Scalability, like easy to scale up and scale down based on the queue length and CPU usage. Resilience, continuous restart automatically on failure, and orchestration handles failover. We deployed a pipeline where each container did one task: resize, enhance, tag, and upload. And with Kubernetes, we scaled to handle a 50 times traffic spike over a weekend without touching infrastructure manually. But even with everything containerized and orchestrated, the performance bottlenecks can still sneak in. That's why the very important things profiling is we need to have for the pipeline maturity. So you can find and fix what's actually slowing down. Like this is the boring part. Like you can just give because it's all about like having the metrics and have the numbers show up and then try to see how they add up. But it's really important. Like don't be lazy on it. Um, like you will regret a lot when not having metrics when you see when you have no clue what's going on. So we are having here. Some common tools for profiling, we have C profile and line profiler in Python, flame graphs, and also some cloud tracing tools such as AWS X-ray, and so for example, in Python, C profile helps you spell time heavy functions. Line profiler shows per line timing, great for pinpoint slowness in loops and image transform. Use flame graphs to visualize which functions dominate CPU time. And in distributed environments, cloud native tracing tool like AWS X-ray, Google Cloud Trace can help identify which microservice or step is dragging the whole pipeline. In one project, we have this image resize operation where we're assumed to be the bottleneck, but for following review, it's actually the file I/O due to using the uh, NFS backed storage, and yeah, fixing that just cuts the processing time in half without any code change. Yeah, performing is about allocating effort where it matters, optimized based on data, not hunches. Um, After that, we have another silent killer of the efficiency, and which is redundant computation. And that's where caching and memorization come in. This is to avoid doing the same expensive work over and over again. Caching and memorization are how we avoid doing the same expensive things twice, especially in pipelines where inputs repeat and the transformation are deterministic. So, to give an example, so the idea was more like if we have already resized or compressed an image once, we shouldn't do it ever again. Instead, we should store the result either in memory or in a local disk cache or in a fast access like Redis or memory cache. For example, we can cache in thumbnails that are reused across pages and the product listing, storing the output of an expensive image embedding model, caching a converted WebP version of a commonly accessed PNG. In production, consider caching layers between processing steps, or writing intermediate artifacts to cloud storage with data, determin, deterministic, sorry, deterministic keys like hashes. Um, this one shift, like adding caching where appropriate, can cut compute costs like drastically, especially under bursty traffic. And once we eliminate like the redundant work, we have our efficient caching mechanism in place. The last step is to have the pipeline with the visibility, knowing when things go wrong, and when things cost too much or the usage trend changed, which is like we talk about observe observability is a very important criteria for this image pipeline. This is more like you have these budget alerts, like you can set like weekly, daily, monthly with your bill if something spikes, and take your resources, like break down so you can break down the cost easily, and so you can check down where, yeah, you can have a better analyze what's going on with the cost. Operation monitors such as CloudWatch, Stackdriver, or Datadog to monitor CPU usage, queue length, and image processing time and error rates. And also set alert for the abnormal specs. For example, if average image processing time jumps by like 3 times, you should trigger like a pager duty alert or Slack. So yeah, with those monitoring and alerting, which can turn our pipeline from a black box into something more controllable system without like we are feeling like flying blind with the pipeline doing everything magic. So yeah, now we'll build an optimized, scaled, and instrument pipeline. The next thing we have to check like is the what image pipeline are hiding. What's the future, ML-driven enhancement, and maybe some ethical questions we need to keep front and center. ML-based image pipelines are already becoming the norm, and we are going to see that trend accelerate over just maybe this year or next year. Um, so it's what kind of this kind of like the major trend right now, like super resolution and denoising. Deep learning models can upscale low resolution images and clean noisy ones in ways traditional filters can't. This means like even low quality inputs can be turned into usable assets. Um, Auto tagging and classification. Embedding models like Clip or VIP can tag and cluster images without human labels, which dramatically reduced manual effort. End-to-end neural compression, end-to-end learned end-to-end learned codec like JPEG AI or DeepSeek BAC are already outperforming traditional formats in both size and quality. This could like become the next generation of AF. But with power comes responsibility. Like these systems are only as unbiased as their training data. If you are auto tagging based on pre-training models, you risk propagating stereotypes. And I'm sure like you heard lots of news about this disaster, like Gemini, even with like Amazon model Alexa showing pages. And there's also issue with the surveillance, like facial recognition, geotagging, and object detecting, raising a lot of privacy flags. Yeah, that's another thing you need to also another thing, yeah, look into beforehand. How the privacy work, what's the privacy policy, what's the legal licensing with this image you want to train on. Yeah, just need to set it clear before you step into something that you're probably not able to afford to. And as the generative AI grows, distinguishing real from synthetic images become harder. Yeah, so that way pipelines will need to track provenance and authenticity. Those kind of things like, yeah, licensing is one thing you can be enforced on. Another thing we do is is uh, be honest with the kind of like intellectual honesty, like be honest about what the image is generated, what the images we use for train for. Be very clear to the customers, like to have the full transparency to the customer about these sort of things. Saying like, oh, we cannot provide everything can be it's real, but we share whatever we know. Just please, if something you find it is not real, flag to us. Yeah, something like that. Um, the point here is not to prevent this from progressing. Is to say like, as the images pipeline evolve, we have to embed those ethical foresight right into the design process, not as an afterthought. Like this kind of mechanism, like in Amazon already see that we have the some legal section, like this ethical or integrity section on the technical design doc about how to protect and be respect these as ethical approaches. So yeah, to wrap it up, for this talk, kind of long. Sorry about that because there's a lot of stuff I have to go through, and lots of interesting examples here. I wish I have more time to share, but it's more like, we go through what's the image data and the current applications, and what's the major challenges. Uh, what's the state of our solution? We start with choosing the image format, compression techniques, leveraging the cloud native service, distributed processing and parallelism, deploy by container containerization and orchestration, and the further optimization and the cost monitoring, and then more modern days we consider about how to preserve the image credibility and integrity of the creators to work through that. Um, so yeah, so although I know it's a bit generic approach about the whole process, but to be honest, like when you start with this can solve like 80% of the problems. And once you have that, you have this efficiency in place. To be honest, I think like while working with this big company, like lots of people actually don't know about this principle at the beginning, and most of them just store a lot of machine and GPU to make the fast performance and spend a lot of money. Uh, but so if you actually know this principle to start with and then follow these things, you can like you can actually beat the average of a lot of the image processing by yourself. Um, but but yeah, after that, of course, there are lots of like niche technique. For example, using Terraform to do the GPU computing to optimize the resources. Yeah, something like that. Yeah, but that's more like more specific component once you get down the baseline. So yeah, let me see. Yeah, I'm good for any questions. Not sure if I can see anything here. I hope everyone can hear me.
Yes, your voice is clear.
Okay.
I think just we can wait for after these if any of them have any questions. Okay, it seems that from the action that it's all fine for them, but we can wait for just 2 minutes if anyone
Mm.
has any.
Yeah, to get the maybe other than this image pipeline processing, yeah, Amazon has been using to process like 10 billions. Like in the end, we were able to like process like 10 million images a day, and in the end, we score all of the images from the internet and training the Amazon Novel, the all the AI model. Um, so yeah, that's kind of like an interesting thing to see the scale. Um, and for now, I'm working UiPath. I work on most the problem set I'm working on is much lower scale, but um, it's lower scale. But we don't have like that much resources to play around, but we have deeper technical stack and the depth to improve the like GPU resources leverage. So it's kind of it's a different approach. Like in Amazon, I've kind of feel like scale horizontally to have the big infrastructure to process the billions of images. But now I was more focused on the technical depth of these GPU nodes optimization. So yeah, it's a bit different right now. Yeah, am I able to? I don't have the material, but am I able to give a talk on that someday? But yeah, if no questions, yeah, do you think we can stop here? Do do you do I have my contact here? So if you, hmm? Sorry, I couldn't hear.
Yes, can you repeat that last question, Anna? Yes, Anna, can you repeat the last question if you can hear me?
Yes.
Yes, feel free to share your contacts with them if you like in the chat.
Don't have it ready yet. Yeah.
Okay, sure. um, we are we will be able to share hopefully with the attendees. And maybe just your name on LinkedIn, Anna Chi, will they find you right away? So Anna Chi and software engineer at UiPath.
Oh, right. Uh, I think LinkedIn, yeah, LinkedIn work. Should be this one. Oh, did I? Where did I put in the question? Sorry. Delete. Technology is hard. Where should I post it? Is it in the chat or?
Or you can just show me on the. Yes, you can directly share it in the chat for the attendees to see it.
Yeah.
And if anyone has any questions, feel free to ask the chat or the Q&A as we still have some more time.
Yeah, it's okay. Don't need to force a question. But might take some time to digest as well. Yeah.
Yeah, thank you so much, Anna.
Mhm.
Sure. So we will be sending the recording on the website after the event. So if anyone would like to see that there, and we'll try our best to send out the contact as well. Okay, so please everyone give a huge clap of these reactions or just thanks for Anna in the chat. Shows some recognition. Thank you really much. Thank you very much, Anna. And for this deep dive. And please feel free for everyone else to join in the upcoming sessions. We'll take a break and we'll get back. So,
Okay. Oh, yeah. I can share slides. Do you know how can I share slides somewhere? Or I send it to the. I definitely send to this event, but I don't know if it's shared to people. Okay. Thank you.
so Anna, the materials are right here. Okay, just let me send and the material for the PowerPoint is also, if you would like to share it, you have a button down which is called share material. You can add it on it, or if you'd like us to share it, you can do that. Just mention this. Thank you, everyone. And last session, and see you later.